Good morning. We're a little bit short-staffed today. I think some folks maybe are going to have a little trouble getting here, but we'll go ahead and get started. First, raise your hand if you lost power at any point in the storm. Raise your hand if you are still without power. So I think this is going to affect a lot of folks around here. I don't think it was as severe as they were predicting. I think the storm turned west before it got as far north as they thought it would. So I think the, kind of like DC and Baltimore, like Jersey, those places got hit a little bit harder, but still it's going to affect us, and I think there'll still be lots of wind today, so just stay safe. We're on page 32, and while you guys open to page 32, we'll take our look at the calendar. Today we talk about probability, which is going to follow nicely from the counting class we did last time. And then next class we talk about chances and odds, very much related to counting and probability. And project number 1 is due, so if you have it, put it in the folder. Some folks emailed me, contacted me, let me know they were having issues because of power outages, and so I've given extensions. So if you don't have the project done and it's because of the storm, just let me know right after class today and we'll work something out, all right? If you don't have the project done but you don't have any excuse, well, do it as soon as possible. I will accept it, but there are lateness penalties that start accruing every day that it's late. It's 5 points off. And that's not just every class, it's every school day, not just Tuesday, Thursday when we have class, all right? So if you get it to me tomorrow, it's 5 points off. Get it to me Thursday, it's 10 points off. And the points keep accumulating every school day. So get it to me as soon as possible. If you get it done on Friday, but we're not going to see each other until Tuesday, email it to me as soon as you can, and then the lateness penalties will stop at that point, all right? So if it's late, it's okay, but there are penalties and you'll want to get it to me as soon as possible. Any questions about anything here? Okay, and then looking ahead, so Thursday we'll talk about chances and odds. Next Tuesday we don't have class. That's November the 6th. It's election day. That's not why we don't have class. We don't have class because it's advising day. And so I will give more detail on Thursday about what advising day is all about. But in any event, there are no day classes that meet on November the 6th. So we won't see each other on Tuesday. We will see each other next Thursday, November 8th for our review. And then the test is 2 weeks from today, okay? 2 weeks from today is our second test. All right, so the first thing we want to look at here on page 32 at the bottom, it says, are there any questions on the how many activity? So this is a while ago now, it was Thursday, but did we have anything we wanted to look at a few pages before? You talked about counting license plates, and there was a question about a lottery. Any questions about anything in here? Mm-hmm. Mm-hmm. Okay, so let's talk about part C. It says, so we have 6-character license plate, just refresh our memories. So we want the license plate to have 3 letters followed by 3 digits, okay? So something like ABC123 is the kind of license plate that we're trying to count. And then in part C, there's some restrictions. So it says the letters O and I and the numbers 0 and 1 may not be used because it could be confusing as to whether you're looking at a letter O or the number 0. So sometimes we'll take them out. And so we want, and it says the same letter cannot be used multiple times. What's that? Okay, we can all see it together. But so let's look at the letters first. So I'm going to write 6 different slots to tell me how many possibilities there are for each slot. So the first thing, is it a letter or a number? First thing is a letter. Always the first thing is a letter. But we can't use O and we can't use I. So how many letters are left over to go in that first slot? 24? Yes, 26 letters to start with, but not O and not I. So there are 24 letters that could go there. And then we're going to multiply. And then the next spot is supposed to be a letter, but it says the same letter cannot be used multiple times. So only 23 letters left. You don't get to use O, you don't get to use I, and you also don't get to use the letter you put in the first slot. So 23 left, and then 22 left once you take away the first 2 letters that you filled in. And then we'll get to the digits. It says we're not going to be able to use the digits 0 or 1. All right, how many digits are there total? Forget the 0 and 1 business, but just how many single digits are there? There are 10 of them. And so it's so 1 through 9 is what most people think of, but there's also a 0 at the start of that list. So there are 10 different digits. Patty, is that what you had? Yeah, forgot about the 0. So normally 10 digits, but you can't use 0 and you can't use 1. So how many digits are left over? 8 times. And then do we go to 7? No, because it doesn't say anything about not repeating the same digit. It only said the letters can't repeat. So it doesn't go down to 7. What does it become? It stays at 8. You can use any digit, not 0, not 1, but you're allowed to use the digit that went in that first digit spot. So this is our answer. Any questions on that one? Okay. All right, so let's move ahead to page 33, and we'll go up here to the top. Can we start with Stephanie for number 2? Okay, we'll go to 3 for Laura. Okay, so let's see how much we know about cards. So the question is, so the card is an ace. That's one possibility when you just pick a card from the deck, right? So the question is, how many outcomes are there that are satisfying this event? How many cards are there that are called an ace? There are 4. Is anybody who's not familiar? It's okay if you're not familiar with that, but is there anybody who doesn't understand the idea that there are 4 aces in the deck? Okay. So then the number of outcomes for that event is 4. There are 4 different things that would count as a success. The card is a spade. It's close to 14. It's 13. Yeah, there are 13 different spades in the deck. There are 13 clubs, 13 diamonds, and 13 hearts. The card is the 2 of spades. How many outcomes are there that satisfy that? Just the one. There's a single card that is the 2 of spades. And then the card is a red spade. Yeah, the spades are black, clubs are black, hearts and diamonds are red, but there are 0 cards that are red and spade. Yeah, we're going to do the out of in just a moment. Right now, we're just looking at the number of outcomes. And right down here at the bottom of the screen, it's going to ask the probability that if you pick a card, it's an ace. And then we're going to do 4 out of something. Great. Okay, let's go to number 4. Where are we now? Is it here, Kristen? Okay, so we talked about, like early in the semester, we talked about percentages, and I'm hoping we see those 2 numbers represent the same thing. 0.1 is the same as 10%. Remember, you move the decimal 2 places to the right. So oftentimes probabilities are given as a decimal. There's a 0.1 probability, or they're given as a percent. Okay, so let's look at this next blank. It says probabilities range from a certain number, which would be impossible, to another number, which represents something which is certain. It's definitely going to happen. So what's the probability of an event that could never possibly happen? It's 0. What's the probability of an event that's certain, that's guaranteed to happen? It's 1, or 100%. So probabilities range from 0 to 1, or equivalently, they range from 0% to 100%. And everything that isn't impossible or isn't guaranteed lives somewhere between 0 and 100%, okay? All right, and here's some notation. Notation for the probability of event E happening is given by this PR of E. It looks like multiplication, but it's not. It's like we would say the probability of event E. So take a look at number 5. We're going to pick a card from the deck. This is what Nicole was asking about. We want to find the following probabilities. So it says the probability that the card is a diamond. We pick one card from the deck. We want the probability that the card is a diamond. So I think most of us understand this is supposed to be a fraction. So what number goes on top? Why is it 13? That's right. So right upstairs, we're going to put the number of diamonds, which is 13. And then downstairs, why are we putting 52? Yeah. The total number of cards goes in the bottom, and that's 52. So if you just pick one card, you have 13 chances for success, diamond in this case, out of 52 chances for anything to happen. Any questions on that number? All right, so with your neighbors, can you answer B, C, and D? And there are 4 people that don't have neighbors. Can we join and pair up 4 folks in the back of the room? Okay, what did we get for part B? The probability that the card is a heart. Same thing, so that's 13 hearts out of 52 total cards. I've written out in black here just the things that we are counting. In this case, it's real easy to just say, oh, I want the number of hearts divided by 52. But in general, probability questions can be really hard. And the first step for a brand new probability question is to figure out exactly what you are counting. Don't dive into the numbers. You got to first know what you're counting before you try to count it. So I'm a big fan of writing out the things I'm trying to count. Down here, the probability the card is black. That's 26 out of 52, good. There are 26 black cards out of the 52 total cards. You're welcome to rewrite any of these things. I mean, 13 over 52 reduces to, yeah, it reduces to 1 out of 4, which as a decimal is 0.25, or as a percentage is 25%. There are a lot of ways to write probabilities. Any of these is acceptable. I'm not going to worry about making you guys simplify fractions on my test. It's fine to leave it as 13 out of 52. It's fine to write any of those things. Okay, and then finally, what did you get for the sum of those 3 numbers? Yeah, so the sum of all these things is 52 out of 52, which is also known as what number? 1, which is also known as what percentage? 100%. Why was it the case that adding these 3 numbers gave us 100%? That's right. Every card in the deck is accounted for somewhere. Every card is either a diamond or a heart or black. And that's it. That describes every single card. And also, every card is exactly one of those things. Right? We don't have any overlap. If we had overlap, we might end up double counting some stuff. But in this case, there's no overlap, and every card is accounted for, so every possibility is up there somewhere. All right, let's go to number 6. Tough word to pronounce. Alex. Good. So if you just pick a card out of the deck, every card has exactly the same chance of showing up, right? No card is favored more than any other. Every card has a 1 in 52 chance of popping up. If you roll a single die and it's fair, meaning it's not weighted towards one side or another, every number has a 1 in 6 chance of coming up. So, okay, so that's equiprobable, where everything is equally probable, equally likely. We'll go to 7, Patty. Good. And so we ended up using that formula a bunch up above without really even thinking about it. And I just want to make sure we're clear. Sample space is vocabulary. It just means the set of all possible outcomes. So I'm going to write the word total down there. It's the biggest number you can find. The number of ways anything can happen. Okay, there are a few more probability questions here in number 8. So there's 2 on this page and several on the next page. Can you guys, with your neighbor, see if you can find all those probabilities? Okay, so part H is the tough one. We'll come back to that one. Let's just jump through some of the easier ones at the start. What's the probability the card is an ace? That's 4 out of 52. How about the card is a spade? It's 13 spades out of 52 total cards. The card is the 2 of spades. That's just a single possibility, not very likely, right? 1 over 52 as a decimal is really close to what nice number? If you typed in 1 divided by 52 on the calculator, you get some decimal. That decimal is really close to a nice number. Patty, what is it? 0.01, and then it goes on, right? What's the next number? What's after 1? 9. Great. That's really close to what nice number? It is close to 2%, yeah. As a decimal, what number is it closest to? Is it close to 1? Is it close to 3? Is it close to, it's close to 0, yes? That number is really close to 0. If the probability of an event is exactly 0, what does that mean about the event? It's impossible. Okay, is it impossible that when you pick one card out, it's going to be the 2 of spades? It could happen. Is it likely? It's really not. And so a number very close to 0 confirms how unlikely it is that if you just pick one card, you'll randomly get that 2 of spades. Okay, the card is a red spade. That's a 0 out of 52, or just 0, because no cards are red spades. The card is black. 26 out of 52. Card is a king. 4 out of 52. Card is a black king. 2 black kings. There's the king of spades and the king of clubs. And then we get to the hard one. The card is black, or it's a king. And it feels to me like we say, okay, there's black cards and there are kings, and I've got those numbers written up above, so let's grab them. So the black cards, we said there were right up here, 26 black cards, and then how many kings? 4. And so it feels to me like the total number of cards that are black or a king is 30 out of 52. What's wrong with that? Yeah, there's some double counting happening here. 2 of the cards in the deck are both black and a king. And so you have counted them in both of these numbers, so you don't get to count them twice. So the probability here is really 28 out of 52. And we'll say it's not 30 out of 52 because there's the king of spades and the king of clubs. So instead of being 30, you subtract those 2 guys back out, we get 28. Is that good? Good. Let's take a look at number 9, Stephanie again. Okay, let's try this one. 2 cards from the deck, doesn't matter the order that they come out. We want the probability that both are red. So first thing I'd like us to do is write in English the things that we are counting. Number of blah blah, number of blah blah. And once we know what we're counting, we'll have a better chance of trying to count it. So let's do the bottom first. That's usually the easier one. What am I looking for down here on the bottom? Number of what? Is that? Is it the number of reds on the bottom? Yeah, it's always a total. It's always a big number down here with no restrictions. So it's the, I'll say total number of, but what exactly are we drawing here? It's 2 cards. So what I want to do is the total number of maybe pairs of cards. Because you said we wanted to pick out 2 cards. Yeah, that's on the bottom there's no restrictions, but the experiment here is picking 2 cards, right? That's the first thing. So I want to know how many ways are there to pick any 2 cards. That goes on the bottom. We're going to figure out how many it is. It's actually not so easy to count how many ways there are to just pick any 2 cards, but we'll count it. But that's what goes on the bottom. What goes on the top is some subset of the number of pairs of cards there are. The things on top have an added restriction. What are we hoping is going to happen on top? Is that they're both red. So then upstairs, we'll put number of pairs of red cards. So the bottom, any pairs you want with no restrictions, could both be red, could both be black, could be one of each, any kinds of pairs of cards. But upstairs, you want to make sure that the pair you pick are both red. Okay, now that we've written in English what we're trying to count, let's see if we can count it. If the cards aren't red, they will count in the bottom number. They won't count upstairs. Up here, when we looked at the probability that the card was the 2 of spades, you had no problem just saying, okay, how many cards are the 2 of spades? It's just one, and we're not going to count the other 51 that don't satisfy that condition. Okay. All right, so let's see if we can count. So we're going to go through our flow chart. You can open it up if you want to. It was page 4 or something in the packet. But I'll refresh your memory with the questions. So the first question we ask ourselves is, are you allowed to repeat? Are you going to get the same card twice in this experiment? No, we're picking a 2-card hand. It doesn't say pick one, look at it, and then put it back. So we can't repeat. And if you can't repeat, that pushes you over to the right-hand branch of that flow chart. Yes? And the next question is about the order. Does the order in which we pick these cards matter according to the question? No, it specifically says it doesn't matter the order. So what option do we need to go with? We have to use combinations. That's what the flow chart says. First thing we said is, are you allowed to repeat? No. Does the order matter? No. The flow chart pushes you into using combinations. That's what we have to do here. So we use combinations since no repetition and order does not matter. I don't know if I would call any of them more common. It really just depends on the setup. Okay, so let's give this a shot. We'll try the number on the bottom first. So the total number of cards, we're picking 2 cards and there's no restrictions on the deck. So when we use a combination, remember it's something C something. How many, yes, the N and the R thing. How many cards are there to choose from? There's 52. You can pick any cards you want in the bottom. And then how many of them are we going to choose? We're going to choose 2 of them. So 52C2 is the denominator. Grace, is that all right? All right, somebody with the calculator, can you help us out here? How much, 26? 1326. 1,326 different ways to just pick 2 cards out of the deck. For example, I'd have the ace of clubs and the 2 of clubs. That's one way, yes? Ace of clubs and the 3 of clubs. That's another way. Ace of clubs, 4 of clubs. That's another way. 3 of clubs, ace of clubs. Is that another way or is that the same? That's the same. Right, we said the order doesn't matter. So there are 1,326 pairs of cards in the deck. I just listed a few of them. Okay. What did you say? 36? Oh, yeah, so if you take 52 and divide it by 2, I guess you're taking like half the deck. We are making pairs, but the first card that you pick, like I'm going to stand here and I'm going to say pick any card, right? So how many cards do you have to choose from? 52. So you're going to take one out. And now this card is your first card. And then I'm going to say pick another card. And you still have 51 things to choose from. So I think cutting the deck in half just to 26 gets us smaller than any of the like number of choices you'll have. You either have 52 choices or maybe 51 if you've already pulled one out. It's the number of cards. It's the total number of cards, but you got to pick 2 of them. So, so I guess I see the word total here in the 52, and then I see the word pairs in the number 2. Yeah. So it's not super important to me how you phrase this thing in the bottom. So phrase it in a way that feels right to you. More important to me is that we can choose combinations as the way to count, and that we can put the right numbers down there. So you can pick any card, and you're going to pick 2 of them. Upstairs, we're still using combinations for the same reason, but here the cards have to be red. So Do another something, see something. I'll do the second number. How many cards are we going to choose upstairs? This is the second number. We're still choosing 2. How do we make sure you only get to pick red cards? If I just said, pick 2 cards and I don't show them to you, are we going to guarantee that you're going to pick only reds? Okay, so what would I have to do physically to this deck so that I could do this? We'll take all the black cards out and we'll only give you the red cards as options. So how many cards would be in the new smaller deck? It would be 26. So if I took all the black cards out and I only gave you options for reds, you put a 26 right there, which is exactly the number of red cards, just single red cards. Somebody have a number for us here? Okay, so the first number was the number of red cards, 26. And we're still picking 2 of them. So then finally putting it all together, probability of getting both cards red, what fraction? That's it. So the probabilities we did up above were so easy, we didn't even have to think about using the flowchart. And we didn't have to think about writing out in English what it is we were counting. Oh, the probability the card is a black king, I can just visualize the black kings. There's 2 of them divided by 52. But we can make the problem tougher, and that's why I'm such a fan of writing out in English what we're trying to count, and then we go to the flowchart to decide how to count. As a decimal, somebody type this in for me? So about 24.5%. It's close to 25, but it is a little bit less. About 20. It depends on where I ask you to round it. I would say round to the nearest 10th, maybe. Okay, what if I just gave you 1 card? I said pick a card. What's the probability that it's going to be red? Just 1 card from the deck. Red is 26 out of 52, which is half, right? So if you just pick 1 card, half the time you'll get red, the other time half will be black. Now suppose you've picked a card out, and let's force it to be red, that one. Now what's the probability that the next card is also red, because we wanted both to be red? It's 25 out of 51. Is it still half? Is it a little more or a little less than half that it's a red card? A little bit less than half, because there are now 25 red cards in here, and because I've taken 1 out. You're not a card person? So it's a little bit less than half the deck is red now. And so if you have half the time you'll get red first, and then a little less than half the time you'll get red second. It's a little less than a quarter of the time they'll both be red. Okay, so here's what we're going to do for the next little bit. We're going to play this game, which was made famous by Monty Hall from the old Let's Make a Deal. Anybody remember that show? I think it might still be running, like there's a new host. I don't know who it is. Maybe it's Wayne Brady. I'm not sure. So what's that? Yeah. So here's the idea. You're at a game show, and I'm going to use my bigger deck for this one. So there are 3 doors in front of you, or 3 curtains, and behind 2 of the curtains is some gag prize, like a donkey or something, and behind 1 of the curtains is a car. So obviously we're shooting for the car. So let me just show you here that here are the 3 curtains. The picture card is going to be the one you want, all right? So this picture is the car, and these are goats or something like that, all right? So we take them, we shuffle them up, and you got doors 1, 2, and 3, and we're just going to pick. Okay, Stephanie, would you like door 1, 2, or 3? Okay, so Stephanie calls number 2. Now, we could just end the game right now and flip it over, and she either has a car or she has a donkey, right? But we're going to make it a little bit more interesting. We're going to say this. Stephanie, I'm going to show you this one. You didn't pick door number 3, and that's a good thing because door number 3 had a goat behind it. I feel like I've changed it between goat and donkey several times. So we've got a goat behind door number 3. So here's the question. Stephanie, would you like to stay with your original pick of door number 2, or would you like to switch over to door number 1? What do you want to do? Right, Stephanie stayed, and she picked the goat, and if she had switched, she would have gotten the car. So here's the question for you. Do we understand how this works? I'm going to do it again, or we got it? Okay, so here's the question. Is it better, so I'm going to, like you'll pick a door, I'm never going to reveal the one that you picked, and I'm never going to reveal a car. I'm always going to show you a goat that you didn't pick, and then ask you to stay or switch. So here's the question. Is it better to always stay? That's what Stephanie did. Is it better to always switch? If she had switched, she would have won the car in this case. Or maybe it just doesn't matter. Talk to your neighbors. Is it always better to stay, always better to switch, or it hardly matters? All right, show of hands, raise your hand if it's better to always stay. Raise your hand if you think it's better to always switch. Raise your hand if you don't think it matters whether you stay or switch. Okay, so everybody's in that camp where it hardly matters, stay or switch. All right, so here's what we're going to do. We're going to pair up, and we're going to play this game a bunch of times. I'm going to give you guys 3 cards for every pair of people. And what you're going to do is, over here on this next page, you're going to record all the results. So one person, let's see, it's a total of 15 times. So one person is going to be the dealer, that's what I was, and the other person will be the contestant, that's what Stephanie was. Do it 15 times in that way, and 15 times the person can either stay or switch, and then change roles, all right? So we're going to have a total of 30 games for each pair of people. Really, really important, what I need you guys to do is keep the data. So there are 4 possibilities here. You can, in the first top left thing, you can stay and win, you can stay and lose, you can switch and win, you can switch and lose. Every game needs to go in one of these boxes. What did Stephanie do? She stayed and she lost. So we put one right there. If we stayed and lost again, we put another one and just start counting them up with those kind of hash marks, okay? You can keep the same, whoever is guessing should be the one to keep score. All right, the other person has enough to do with playing with the cards. So if you're the contestant, you keep score. Again, the picture card is the car. That's the one that you want. So pair up. Who are my pairs here? Here. There we go. Okay. So we've got lots of trials up here, way more than just the one that we demonstrated where Stephanie was the contestant. So what I want to do is now just get a total for each of these slots. So can we have some folks add things up and we'll get confirmation? That's a 27. Is that 42? Okay. And over here, is that 30? All right, so just double check, make sure we have all the data right. Okay, Patty? Oh, all right. So here's the data. Now, every person in this room was content to say that it was pretty much a 50-50 whether you stayed or switched. You'd win the same amount as you lost. Just take a look at the first row right here where we stayed. When we stayed, we won 30 times and we lost 42 times. Is that 50-50, better than 50-50, or worse than 50-50? This is worse than 50-50. So if I wanted to figure out what the probability is that if I stay, I win, it's 30 out of what number? I want the probability that we're going to win if we stay. It's 72 down here because you guys did that 72 times. So out of a total of 72 times when you stayed, you won 30. Can somebody get me a percentage? Just type that in. About 42%. That's fine. Thank you. Okay, so we did not do 50-50 in that row. And what if we look at the switching and winning? What's my fraction here? Yeah, I want to win, so 27 wins out of 42 times we played. Is that better or worse than 50-50? That's a lot better than 50-50, right? You guys came out ahead way more than you lost when you switched. Somebody get me a decimal here? 64? We did switch a lot less, so maybe you'd want to do more data collecting where you try to even out these numbers. But it sure did not seem 50-50 in either time. It felt like if you stayed, your your chances of winning are a lot less than 50-50. And if you switched, you got almost a 2/3 probability of winning, which is interesting. Okay, so here are the theoretical numbers. This is just data, and the data doesn't always tell exactly the right story. But I will tell you that if we did this experiment like thousands and thousands of times, the probability that that you win when you stay is 33 1/3%. That's the true probability. If you stay, you will win 33 1/3%. Did we do better or worse than the true probability? We did better. You guys won 42%. Really, by rights, you only should have won 33%. Now, I happen to have witnessed some shenanigans over here in this table where Laura apparently does not have a good poker face, and so Kristen was able to read a little bit of what Laura was saying. So perhaps that's why the numbers are skewed a little higher than they should be. And then down here, I will tell you that the probability that you win should be exactly 66 2/3%. So we were very close to the right number on that one. So how is it that it's not 50-50? It's really surprising because, so we'll just play this game once up here. All right, so we'll go to Kristen, the card shark in the room. 1, 2, or 3? Okay, so I'm going to show this one. Now, how many cards are left unexposed at the moment? There's 2, and how many of them are winners? 1. So it feels like 1 out of 2, she's going to pick the right one, right? Did you want to stay or switch? Staring at me. Do you see this? Like looking right through me. What do you want to do? Switching to the middle, right? So so I'm not going to play poker with Kristen. So it feels like it's a 1 out of 2 in both cases. It's a 1 out of 2, whether you stay or switch. So how is it that the numbers that we expect are so far off from reality? All right, I'm going to try to convince you that it's a 1/3 and a 2/3 no matter what. And I'm going to try to convince you in a couple of different ways because this result that we're getting here is so counterintuitive that that we really need a lot of convincing, I think. Okay, so let's play this game again. So we've got 1, 2, and 3. We'll go with Alex. What do you want? Okay, so 3 is this one. Okay, so here is the choice. Instead of revealing one card, let me give you a different option, a different way of thinking of it. Alex, would you rather stay with this one or switch to both of these, and if there's a car behind either one, you get it? What would you do? Do you want to stay with your card or switch to the other 2 doors? All right, was this the wise choice, probability speaking? It's pretty clear you want to switch, right? Now, in this case, staying is the right choice, but it hardly matters. It hardly matters what the cards are. If I give you the option of would you rather have one door or the other 2, you're going to pick 2, right? And that's equivalent to this game that we played because Alex picks door number 3. I'm going to show you one of these cards. Let's say it's this one. And then when you say switch, you get the other one. So if there's a car behind either of these, you're going to find it when you switch, right? Do you see that? Like the only way that staying is the right choice is if we happen to pick it first. Yeah, what's the probability that Alex picks the card first? It's 1 out of 3. There's right, it's just 1 out of 3. So if you stay, you're still going to be 1 out of 3. It doesn't matter what I show you over here. But if you switch, I'm giving you a chance to take the other 2 doors, not the one that you picked. And it sure feels better to me to pick the 2 doors instead of the 1. Let's come back to that 1 out of 3 business. So Alex has picked a door. I show this one, and now it feels like it's a 50-50 because there are 2 cards left, and one of them has the car and the other has nothing. But it's not 50-50. If you stay with the door that you have not responded to the information that I've given you. Your probability, the stuff hasn't magically moved around back here, right? It's staying where it is. You had a 1 in 3 shot of picking it right the first time. And if you stay, nothing changes. You have not acted on the new information. So it doesn't bump up magically to 50-50. The goat and the car are still back here where they were before. So it's 1 out of 3 if you stay. It's a 2 out of 3 if you switch. Let's think of it this way. Let's see. So we got 1, 2, and 3. And let's go ahead and represent the car with a dollar sign. And just for the sake of argument, let's say that we pick door number 2 consistently. Every time we'll pick door number 2, and it's the same argument for picking a different door. But let's just pick door number 2. And here are the 3 possibilities, right? Either the car is behind 1, or the car is behind 2, or the car is behind 3. So every possible game is up here. And we're going to focus on door number 2 every time. Okay, so let's keep track of what happens if we stay and what happens if we switch. So if we're in the first row, where's the car? Behind door number 1. Now you're going to pick door number 2 every time. So if you pick door number 2, what do I have to reveal? Which door? I have to show you the blank behind number 3. I can't show you the car, right? So if you stay with door number 2, do you win or do you lose? You lose. But if you switch, remember I've revealed door number 3. So if you switch, I'm forcing you to take the car, right? So staying in this case makes you lose. Switching makes you win. Let's go to the next one. Where's the car? It's behind 2. Now we're just going to pick 2 every time to be consistent here. So if you stay with 2, what happens? You win. That's a good choice. So if you stay, you win. What door would I reveal to you? Oh, thank you. So if you stay, you win. So if I wanted to show you a door, I could show you 1 or 3. It doesn't matter, right? And if I show you 1 and you switch to 3, you lose. If I showed you 3 and you switch to 1, you lose. So the only way you win is if you stay. And if you switch, I'm forcing you to go off the car. So right now it feels like a 50-50. If you stay, half the time you'll win and half the time you'll lose. But there's a third game we haven't looked at. This one on the bottom. So the car is where? It's behind 3. You're picking door number 2 just to be consistent. If you stay with 2, what happens? If you stay with 2, you lose, right? If you stay with 2, you lose. What do I have to show you? Which door? I have to show you the blank behind 1. And if you switch, I'm forcing you to find that car. All 3 possible games are up here. If you stay, how many times do you win out of 3? Just once. If you switch, how many times do you win out of 3? Twice. That make sense? So counterintuitive. Like it just feels like 50-50 and it couldn't be anything else. But it's not. It's a 1 out of 3 if you stay. It's a 2 out of 3 if you switch. And I wanted to show you one more. This is kind of an extreme version of this game. All right, so I've got a whole bunch of cards up here. All of them are blanks except for the 1 King of Hearts. You can see it right there, okay? So this is a game with like 30 doors, and you're going to pick one of them, and then we'll show you something, and then you can stay or switch, all right? So let me just first shuffle things around here. Okay, so lots of, oh, sorry, there was an extra car hiding behind one of the doors. So the only car is the King of Hearts. All right, so Grace, can you just touch one of these cards? Okay, so Grace has touched this one right here. Now I'm going to give a different game. I could reveal one, like I could just reveal one door, but then the idea of staying or switching doesn't make sense, right? Because what does it mean? So here's what I'm going to do. I'm going to leave the door that that Grace picked unexposed, and randomly I'm going to leave one other door unexposed. It happens to be this one right next to the one that she picked. And then I'm going to hold these 2 here, and I'm going to show you all the blanks in the other 28 doors, or however many there were, okay? And now the question is, do you want to stay or do you want to switch? Keeping in mind that the one random door you picked is still closed, and then this other door somewhere else in the list of 30 is closed, but behind the other 28 doors, lots of donkeys. So what do you think? Would you stay or switch? Tim says switch all day, and that feels like the right thing to me, right? Because there were 30 doors up there. There's only 1 in 30 chance that you picked the one that had it. And if I'm going to reveal all these donkeys except for your donkey and the car, switch all day. And that's kind of what this game is saying too. What do we think? Good? You could win some money on, so don't win money on this, but it is so counterintuitive. Right. All right. So here's what we're going to do. If we go back to page 30, so I know we didn't have time in class to do this, and if you did a bunch of it after class, good for you. But on page 30, I'd like you guys in your groups to work through as many as you can of number 2. So go back to page 30. Number 2 has all these different counting things. It's not probability, so there's no fractions. We're just trying to decide, do we multiply, do we use permutations, do we use combinations, and just see how far you can get on these on page 30.